Welcome back to the last lecture of 11th week. We are now sort of nearing the end of the course, which I am sure you are quite happy to be. It's an easy course, but pretty heavy. You have learned a lot of new things, which you must admit and appreciate. So, last couple of lectures we have been broadly talking about heat of reaction, and we also came across terms like heat of formation, heat of combustion, etc., etc. The primary objective what we have been looking into, what is the major difference from the initial part of the course where we were talking about energy balance. We were actually looking at energy balance of non-reacting system. For example, when a steam was condensing in steam chest, or you were taking or breaking a ampoule of liquid in a excavated tank, there was no chemical reaction. And now the moment you talk about chemical reaction, you need to consider the thermochemistry or the thermal effects of chemical reactions, and which we have been learning. So, one specific term that we have already encountered is heat of combustion, which is nothing but essentially the heat of reaction of combustible material. In today's lecture, if you look into the title, we will be talking about heat of neutralization. Now, heat of neutralization is nothing but the neutralization reaction. You all know that there is neutralization reaction that takes place between acids and bases, and so essentially when an acid reacts with a base, it is called the neutralization reaction, because the base neutralizes the acidity or the acid neutralizes the basicity and stuff like that, right. So, what is heat of neutralization? Even before we write it, the class actually knows. It is essentially the heat of reaction between or a neutralization reaction between an acid and base. So, let us consider a specific case of neutralization, and I am going to show you something very interesting. Neutralization of a dilute aqueous solution, of NaOH with a dilute solution of HCl. So, the concerned reaction, the associated chemical reaction is of course, we all understand NaOH aqueous plus HCl aqueous leading to NaCl aqueous plus H2O liquid, right. So, there is nothing exceptional or great in this whole concept, we all know about it. Now, there is some additional data. Let me provide you with some additional data. We know the following heat of formations formation data are given, right. So, it is like for NaOH aqueous minus 112.236 kilocalorie per gram mole. Similarly, for HCl aqueous, the heat of formation NaCl, you do not have to remember anything for your examination or whatever, all this data will be provided, it is not for you to remember. Kilocalorie per gram mole. I am just showing it because these data, it is a little boring when I am writing this data, I am just copying it from my own notes because I also do not remember. And that is actually an important thing for all of you to know, that more than remembering some values, if you just know where you can locate these values or you can estimate these values if there are some formula, right, that is the more important thing. That is the basic philosophy. I mean, we all know that many of you actually try to remember stuff to your memory, even data, which is actually not required. You just need to know where I can find this data. So, if this be the case, then since all the heat of formations are known, therefore, the heat of reaction for this particular reaction can be easily found out. And it turns out to be minus 13.360 kilocalories, which is fine. So, you get some value for the heat of neutralization. So, this heat of reaction is actually nothing but the heat of neutralization. And though just 2 minutes back I was telling you not to remember any value, it turns out that this particular number is quite interesting. Well, let us see how. So, we now understand what is heat of neutralization, and now so heat of neutralization can be directly measured actually based on calorimetric measurements. How you do that? You can read the texts. I won't go into the details of the experimental procedure. Again, it's that thing that you know that it can be measured based on some calorimetric measurements. You can open an experimental chemistry textbook and find out how it is done. So, agreeing to that, let us now look into the heat of neutralization of some other acids and base, or between some other heat of neutralization or heat of reaction of neutralization reaction between some other acids and base. And let us right. And it turns out that, let us say, if we are talking about the neutralization between hydrochloric acid and LiOH, lithium hydroxide, you get LiCl and H2O. You can have neutralization, let us say, between nitric acid and potassium hydroxide, right, which leads to KNO3 plus H2O. You can have, let us say, neutralization between sulfuric acid and potassium hydroxide, sodium hydroxide, whatever you feel like, right. And theoretically, you can calculate, or in principle, based on all the discussion we have had so far, you can calculate the heat of neutralization in each case, provided you know the heat of formation of each of the constituents, right. Well, there is a crack. Now, there is the crux. It turns out that the heat of reaction for this particular neutralization reaction is minus 13.36 kilocalorie. This one minus 13.350 kilocalorie, or maybe I will use an approximately equal to sign to be absolutely clear, because the data may vary from case to case. and this one turns out to be again. So, it is actually a perfectly valid question that I provide the heat of formations of these compounds and ask you to find out the heat of neutralization of any one of the reactions. Yeah, it turns out, so here is a take home message. The heat of neutralization, what is the take home message? Can anybody guess? Had it been a class, I would have actually paused for a couple of minutes, allowed the class to respond, and I would have dug out the answer amongst the students. Now, so what is the take home message? The take home message is the heat of neutralization between a strong acid, I guess all of you remember what is a strong acid, and a strong base is constant. This is the first level knowledge, it is constant, right, and this again one can remember this and you will be considered knowledgeable, but that is not what we intend to do. The moment we have an unique observation, you should train your mind to ask the right question, and in this particular case the right question is why, right. What exactly is happening between amongst all different combinations of strong acid and strong bases that their heat of reaction or the heat of neutralization is constant. So, you must ask yourself what exactly is happening. So, what exactly is happening is actually attributed to the property of strong acids and strong base. And what is that property? Strong acids and strong base in an aqueous solution, we all know, remain fully dissociated or get fully dissociated. So, whenever you are taking, let us say, HCl, or maybe in the previous slide, let us say, yeah, here also we had HCl or NaOH, what we actually have, right. So, let me just write it. So, when you are writing the equation, we know that a strong acid will remain fully dissociated, a strong base will remain fully dissociated, right, and a salt of a strong acid and a strong base, which is sodium hydroxide in this particular case, in an aqueous solution will also remain fully dissociated. So, this NaOH actually remains in the form of Na plus and OH minus, HCl remains in the form of H plus and Cl minus, NaCl remains in the form of Na plus and Cl minus, right. So, therefore, when you put this acid and base together, the actual chemical reaction that is happening is Na plus Cl minus plus H plus Cl minus is equal to Na plus, all in aqueous medium, plus H2O liquid, right. And what we actually understand that, sorry, I must correct it, it is OH minus. If you just think, again sorry, that Na plus and Cl minus cancels out, the net reaction that you actually have is H plus OH minus leading to H2OL. So, and you can yourself, so this is the effective reaction as Na plus and Cl minus, right, remain dispersed as ions, right. So, what is the genesis of Na plus? Na plus comes from NaOH, but once it enters the aqueous medium, it now is in the form of Na plus. Though effectively it forms NaCl by reacting with HCl, right? Why does it actually form? Because in the ionic state or within the aqueous medium, it forms Na plus and OH minus. HCl forms H plus and Cl minus. Now, the OH minus and H plus are gone. They are combining to form water, as you can see the effective reaction, right. So, essentially the two charged species that are actually left are Na plus and Cl minus, and when you remove the water, it forms NaCl. That is how it goes. So, for all the reactions that we have written above, if you write them or if you consider the dissociation of the acid, the salt, the base and the salt, the effective reaction that actually happens in each of the case of this neutralization is a reaction which is H plus plus OH minus is equal to H2L. And therefore, in all cases there is now no doubt, I guess all of you understand why in all cases the heat of neutralization is same. Does it mean that it is universally valid for all types of acids and bases? The answer to that is no. It is only valid for strong acid and strong base which fully dissociates in an aqueous medium. So, anything we can conclude if you have a weak base, weak acid or whatever. Now, the moment, so you can have either a weak base and a weak acid, or you can have a weak base or a strong acid or whatever. But the moment you have one of the components which is weak, it does not fully dissociate, it undergoes partial dissociation. And the moment there is partial dissociation, either the cation or the supply of the cation or the anion is restricted, and therefore, you cannot have a complete reaction of all the H plus ions and OH minus ions reacting to H2O. So, therefore, the numerical value of the heat of neutralization for any neutralization reaction which involves at least one weak component, either a weak base or a weak acid, is going to be numerically lower than 13.36. It does not really matter whether you have both are weak or just one is weak, because whichever is going to be the weak one, that is going to limit the supply of the cation and anion, right, and that limits the extent of water molecules that will form. So, essentially, as we were talking in the context of a reaction with partial completion, the moment you have a weak acid or a weak base, this sort of becomes a situation of a chemical reaction with partial conversion, right. So, it is something like that. So, this is what I wanted to talk about. So, one can look into the neutralization reaction of hydrocyanic acid, for example. This you do not have to remember again, let me tell you just for the sake of completeness. Hydrocyanic acid with NaOH, it is HCN. The heat of neutralization is minus 2.481 kilocalorie. And now, I guess you all understand what is the reason why you have a lower value of the heat of neutralization. Okay. So, that is easy actually, but it is very interesting that the heat of neutralization between all strong acids and strong bases have exactly the same value. Next, what we talk about is another very interesting case study, another interesting case, that is essentially the thermoneutrality of salt solution. So, it is also something many of you actually know. So, essentially when dilute aqueous solution of two neutral salts are mixed, there is almost no thermal effect. The reason for that we will understand in a minute's time, provided there is no precipitation or evolution of gas, right. So, it is something like this, let us say NaCl plus KNO3, and the reason for this occurrence is exactly what we discussed in the previous context, and the heat of reaction is nearly equal to 0. So, what type of salt is NaCl? It is a salt of a strong base and a strong acid. So, therefore, in an aqueous medium this will remain fully dissociated, and Na plus and Cl minus. Same with KNO3, it will remain dissociated with K plus and NO3 minus. NaNO3, well, and this one K plus and Cl minus. So, if you look into the ionic reaction, what happens is Na plus aqueous plus Cl minus aqueous plus K plus aqueous plus NO3 minus aqueous, leading to Na plus aqueous plus NO3 minus aqueous plus K plus aqueous plus Cl minus aqueous, and you can see there is actually no reaction, right. So, therefore, obviously, the heat of reaction gets 0, and if you treat this as an algebraic reaction, you cancel the terms from both the sides, you actually get an identity 0 equal to 0, right. So, this is what is known as thermoneutrality of salt solutions. So, when you mix two salts which are both salts of strong acid and strong base, right, there is no thermal effect. Of course, again, if you have a salt of a weak base or a weak acid into the system, there will be some small thermal effect, right. You understand that, because there will be some partial dissociation. Okay. Now, one interesting question, if you have a salt mixture like this, which is in an aqueous solution, and the water is slowly evaporated, or you dry the salt, right. So, you have this in a bath of water, you have this a mixture of salt 1 and salt 2, right, you have added. So, let us term this as salt 1. This is salt 2, this is salt 3, this is salt 4. So, what do you expect? And then we slowly evaporate water, right. And so, what are you expected to get back? You get deposit that comprises all 4 variety of salts. What are the varieties? So, you have NaCl, you have KNO3, you have NaNO3, and you have KCl, all the 4. And anybody knows what this phenomena is called? This is what is called the double decomposition of salt. Right? This is what is called the double decomposition or salt, or it also has another name which is not that frequently used. It is called metastasis, right. So, this is what it is. This is what is known as the double decomposition of salt or metastasis, right, and I guess it's obvious and very clear to all of you. So, we have learnt about heat of neutralization between acids and base, and we have also learnt about the thermoneutrality of salts. Now, what I am going to pick up, and if I am unable to finish it in today's this particular class, we will continue till the next class, is a hypothetical concept, very useful concept, which is known as the heat of formation of ions. So, let me repeat, it is a hypothetical concept, but it does not really matter, because your whole business of heat of reaction, heat of formation actually rests on the fact that all elements have in their natural form have heat of formation is equal to 0. So, there is already lot of assumption. So, there is again there are going to be some assumptions when we talk about the heat of formation of ions. Let us have a look how it goes. So, what we have got is from the previous lesson that the heat of neutralization or in even simpler terms the heat of reaction minus 13.360 kilocalorie for this reaction. Right. So, this is what we have got from the previous lesson, and we also know that the heat of formation of water is minus 68.317 kilocalorie. So, what would that mean? That means the heat of formation, heat of reaction of this particular reaction is minus 68.317 kilocalorie. Now, if we sort of write, if we just combine these two equations, again Hess law coming into the picture. So, we have H2 plus half O2 leading to H2O, and H2O as if we consider it is dissociating to H plus and OH minus. So, this is exactly the situation like the way we calculated the heat of formation of carbon monoxide. So, first what we took the formation reaction of carbon dioxide. So, C plus O2 equal to CO2. Then we looked into the oxidation reaction of carbon monoxide, CO plus half O2 equal to CO2. We found out the heat of reaction there, and then we wrote it in a form as if CO2 equal to CO plus half O2, right, and the heat of reaction just got reversed. So, if we write like this, the neutralization reaction we write like this, then obviously from Hess law we understand that its heat of reaction is going to be minus 13.36 kilocalorie. And if you now join them up following Hess law, you sort of get, you get this particular equation and its heat of reaction turns out to be minus 68.317 plus, right, 13.36. Right. So, it obviously it is plus because it is minus of minus, and therefore, it is plus, and it turns out to be minus 57 point, or sorry, minus 54, turns out to be minus 54.957 kilocalorie. Right. So, what exactly is this value? So, this you now see this we can consider, this reaction we can consider as the formation reaction of H plus and OH minus ions together. Why? Because after all, in this as per this particular reaction, these two ions H plus and OH minus are getting generated from their constituent elements in their standard form. I repeat, though we are running out of time, I will repeat. See here, when we talk about the formation reaction of water, we are essentially talking about generation of water from their constituent elements in their standard form, right. Then we applied Hess law essentially over here, and we have got this reaction which sort of gives us the feeling that it is the formation reaction, as I have written here clearly, it is the formation reaction of H plus and OH minus ions together from their constituents in their standard form. So, here I stop this particular lecture at this point of time and continue in the next class. Here, as if we now have the combined value of or heat of formation of H plus and OH minus ions. So, heat of formation of these two ions together. So, this particular thing HR 0 is, you can consider heat of formation of H plus or the combined heat of formation plus and OH minus ions. So, I stop here and finish the remaining part of the heat of formation of ions in the next class. Thank you very much.